4.6 billion years ago, Earth began an incredible journey that shaped the world we know today. At first, it was a blazing ball of rock with no oceans, no air to breathe, and no living things. Over countless ages, the planet slowly cooled, continents formed, seas appeared, and the first tiny forms of life emerged. Life continued to change, filling the oceans, spreading across the land, and giving rise to giant forests, mighty dinosaurs, and eventually humans. Every mountain, river, desert, and ocean carries the marks of this long history. The birth of Earth and the early solar system began long before there were oceans, continents, plants, animals, or even a solid planet. It started inside a large cloud of gas and dust drifting through a part of the Milky Way galaxy. This cloud was made mostly of hydrogen and helium, the two lightest elements in the universe. It also contained tiny amounts of heavier elements such as carbon, oxygen, silicon, magnesium, iron, calcium, aluminum, sulfur, and nickel. These heavier elements had been formed inside older stars during their lives and were spread into space when those stars reached the end of their existence. Over a very long time, this cloud slowly changed as gravity pulled its material closer together. As gravity continued pulling the gas and dust inward, the cloud became smaller and denser. The particles inside the cloud moved faster as they came closer together. Small pieces of dust often bumped into one another. Some collisions were gentle enough for the particles to stick together. Tiny grains slowly became larger grains. These larger grains continued gathering more material. At the same time, the center of the cloud became hotter because of the growing pressure caused by gravity. More and more material gathered in the middle, creating a young star that would later become the Sun. The growing Sun was not yet shining as it does today. During its earliest stage, it was surrounded by a wide, flat disk made of gas and dust. Scientists call this a protoplanetary disk. This disk stretched across a huge area around the young Sun. Inside the disk, countless small pieces of rock, metal, and frozen material moved around the center. They traveled in nearly the same direction, while following paths shaped by gravity. The disk was not completely smooth. Some places had more material than others. These crowded areas became important because they allowed larger bodies to form. The temperature inside the disk was very different depending on the distance from the young Sun. Close to the center, the heat was extremely high. Only materials with very high melting points could remain solid. Metals such as iron and nickel, along with rocky materials rich in silicon and oxygen, stayed solid while lighter materials remained as gases. Farther away from the Sun, temperatures became much lower. Water, methane, ammonia, and other substances could freeze into solid ice. Because of this difference in temperature, the inner solar system became rich in rocky planets, while the outer solar system gathered large amounts of ice and gas. Small dust grains continued sticking together. Static electricity helped some of the tiniest particles cling to one another. As they became larger, gravity became more important. Objects that reached several kilometers across attracted even more material. These growing bodies are known as planetesimals. Millions of planetesimals filled the early solar system. They frequently collided with one another. Some impacts broke them apart, while others caused them to join together. Over time, the larger bodies became even larger because their stronger gravity pulled in nearby material. The process of growth continued for millions of years. Larger objects, known as planetary embryos, formed from the repeated joining of planetesimals. These embryos traveled around the young Sun while affecting one another through gravity. Their paths often crossed. Large collisions became common. Every impact changed the size, shape, and movement of these growing worlds. Some embryos disappeared after crashing into larger neighbors. Others survived and continued gathering more material until they became planets. Earth began as one of these growing rocky bodies. It was not born fully formed. Instead, it slowly grew through countless impacts with smaller objects. Every collision added more rock, metal, and minerals. As Earth became larger, its gravity also became stronger. This stronger gravity allowed it to pull in even more material from the surrounding disk. During this stage, Earth was a violent and active place. Huge impacts released enormous amounts of energy. The heat from these collisions, together with heat produced by radioactive elements and pressure inside the growing planet, caused much of Earth's interior to melt. When much of the young Earth became molten, heavy materials moved toward the center, while lighter materials rose toward the surface. This process is called planetary differentiation. Iron and nickel, being much denser than most rocky minerals, slowly sank through the molten rock until they collected deep inside the planet. These metals formed Earth's core. Lighter materials, rich in silicon, oxygen, aluminum, calcium, sodium, and potassium, remained closer to the surface, forming the mantle and the earliest crust. Earth's core became divided into different parts as the planet continued cooling. The deepest part became the inner core, while the outer part remained liquid because of the extremely high temperatures. The movement of liquid iron inside the outer core later became responsible for creating Earth's magnetic field. This magnetic field would eventually help protect the planet from many charged particles coming from the Sun. The young Earth looked nothing like the world people know today. Its surface was covered by large areas of molten rock. Volcanoes were extremely common. Huge amounts of lava flowed across the surface. The crust repeatedly formed, broke apart, melted again, and reformed. Large impacts from space continued striking the planet. Every major collision added more heat and often destroyed parts of the early crust. One of the most important events in Earth's early history happened when a large planetary body struck the young planet. Scientists believe this object was about the size of Mars and is often called Theia. The collision released an enormous amount of energy. Large amounts of rock from Earth's outer layers and from the impactor were thrown into space. Much of this material remained in orbit around Earth instead of escaping completely. The rock and dust circling Earth gradually came together because of gravity. Smaller pieces collided and joined with one another. Over time, these materials formed a single large body. This body became Earth's moon. The formation of the moon happened relatively soon after Earth's birth. Studies of moon rocks collected during space missions support the idea that the moon formed from material shared by both Earth and the impacting body. The presence of the moon greatly affected Earth's future development. Its gravity influenced Earth's rotation and helped stabilize the direction of Earth's axis over very long periods. The moon also became responsible for strong ocean tides after Earth's oceans formed. These effects continued shaping Earth's environment for billions of years. After the giant impact, Earth remained extremely hot. Much of its surface was once again molten. The planet slowly cooled over millions of years. As temperatures dropped, solid rock began forming on the surface. The earliest crust was thin and unstable. It frequently cracked because of volcanic activity and impacts from space. New molten rock rose from below and replaced older crust that had broken apart. During this time, Earth's atmosphere was very different from the air people breathe today. The first atmosphere probably contained mostly hydrogen and helium gathered from the solar nebula. Because Earth was still small and very hot, much of this early atmosphere escaped into space. The Sun also produced powerful streams of charged particles that helped remove these light gases. A second atmosphere gradually formed through volcanic activity. Volcanoes released huge amounts of water vapor, carbon dioxide, nitrogen, sulfur compounds, methane, ammonia, and other gases trapped inside Earth's interior. These gases collected above the surface and formed a much thicker atmosphere. Free oxygen was almost completely absent during this early stage. The atmosphere would remain without significant oxygen for a very long time. Water played an important role in Earth's early history. Much of Earth's water came from gases released by volcanoes. As the planet cooled further, water vapor condensed into liquid water. Rain fell over long periods, filling low areas and creating the earliest oceans. Additional water may also have arrived through impacts from water-rich asteroids and other small bodies traveling through the solar system. The first oceans were different from today's oceans. They were warmer because Earth's interior released much more heat than it does now. The atmosphere also contained much higher amounts of carbon dioxide, helping trap heat. Minerals dissolved into the water from newly formed rocks. Chemical reactions between seawater and the crust slowly changed both the oceans and the atmosphere. The early sun was slightly less bright than it is today. Even though it produced less energy, Earth remained warm enough for liquid water to exist because greenhouse gases in the atmosphere helped keep temperatures above the freezing point across much of the planet. These gases included carbon dioxide, water vapor, and probably methane. The young solar system contained many leftover objects that had not become planets. These included countless asteroids, comets, and smaller rocky bodies. Their paths often crossed those of the newly formed planets. As a result, impacts remained common for hundreds of millions of years. Earth, the Moon, Mercury, Mars, and other rocky worlds all experienced repeated collisions. Scientists study the Moon to better understand this period because the Moon has preserved many ancient impact craters. Unlike Earth, the Moon has almost no atmosphere, flowing water, or active plate movement to erase these marks. Many of the large circular basins visible on the Moon today formed during this early period of frequent impacts. Earth's surface has preserved far fewer signs from its earliest history because geological activity constantly changes the crust. Wind, rain, rivers, oceans, volcanoes, earthquakes, and plate movement have destroyed or buried much of the oldest evidence. Even so, tiny mineral crystals known as zircons have survived from Earth's earliest times. These crystals provide valuable information about conditions on the young planet. Scientists determine Earth's age using radioactive dating. Certain radioactive elements slowly change into other elements at steady rates. By measuring these changes in rocks and minerals, researchers can estimate when they formed. Studies of Earth's oldest minerals, moon rocks, and meteorites all indicate that the solar system formed about 4,540,000,000 years ago, with Earth forming shortly afterward. Meteorites provide especially important clues because many have remained largely unchanged since the solar system first formed. They preserve materials from the original cloud of gas and dust. By studying their chemical makeup and radioactive elements, scientists learn about the conditions present before the planets fully developed. Not all meteorites are alike. Some are mostly rocky, while others contain large amounts of iron and nickel. A few contain both rock and metal. These different types formed in different environments during the early solar system. Some originated from bodies that melted and separated into layers much like Earth did, while others remained mostly unchanged after their formation. gravity remained the main force shaping the solar system throughout its early development. It controlled the movement of planets around the Sun, moons around planets, and smaller bodies throughout space. It controlled the movement of planets around the Sun, moons around planets, and smaller bodies throughout space. Every object with mass attracted every other object. The larger the object, the stronger its gravitational pull became. This simple rule guided the growth of planets from tiny dust grains into worlds thousands of kilometers across. As the planets formed, they influenced one another through gravity. Their movements slowly changed over time. Some small bodies were pushed into different orbits. Others were thrown completely out of the solar system. Some crashed into planets or the Sun. These interactions gradually reduced the amount of loose material remaining between the planets. The giant planets also played an important role in shaping the solar system. Jupiter became especially important because of its enormous mass. Its gravity affected the movement of countless asteroids and comets. Some objects were pulled toward Jupiter while others had their paths changed and travelled toward the inner solar system where rocky planets like Earth were located. The asteroid belt formed between Mars and Jupiter. Scientists believe Jupiter's strong gravity prevented this material from joining together to form another planet. Instead, countless rocky bodies remained separate. Many still orbit the Sun today, although collisions among them continue to create smaller fragments. Farther from the Sun, icy objects collected in distant regions. These areas became home to countless frozen bodies that remain part of the solar system today. Some of these objects occasionally move towards the inner solar system, appearing as comets, with bright tails when sunlight heats their icy surfaces. The Sun itself continued changing during Earth's earliest history. After enough hydrogen gathered in its center, temperatures and pressures became high enough for nuclear fusion to begin. Hydrogen atoms joined together to form helium while releasing enormous amounts of energy. This energy spread outward and eventually reached space as sunlight and heat. From this point onward, the Sun became a stable star capable of shining for billions of years. Solar wind continued flowing outward from the Sun. This stream of charged particles helped clear away much of the remaining gas left from the original solar nebula. Once this gas disappeared, planet formation slowed because less loose material remained available. The basic structure of the solar system had largely taken shape. Earth continued cooling inside as well as outside. Heat trapped during formation slowly escaped toward the surface. Radioactive elements within the planet continued producing additional heat. These energy sources kept much of Earth's interior active. Molten rock deep below the crust remained able to move slowly over very long periods. The earliest crust was probably made mostly of dark volcanic rocks, rich in iron and magnesium. Over time, repeated melting and cooling created lighter rocks, containing more silicon and aluminum. These lighter rocks eventually formed the earliest continental crust. The first continents were much smaller than those existing today, and changed greatly through volcanic activity and crustal movement. Plate tectonics, the slow movement of Earth's outer shell, probably began during the planet's early history, although scientists continue studying exactly when it started. This movement recycled crust into the mantle, created new crust through volcanic activity, and slowly shaped the surface into changing continents and ocean basins. Earth's magnetic field became another important feature during this early period. The movement of liquid iron inside the outer core generated electric currents. These currents created a magnetic field extending far into space. The field deflected many charged particles coming from the Sun, reducing the amount of harmful radiation reaching Earth's atmosphere. Without this protective magnetic field, the atmosphere could have been lost much more quickly to space. Mars provides an example of a planet that lost much of its global magnetic field early in its history. As a result, much of its atmosphere gradually disappeared over time, leaving a much thinner blanket of gases around the planet. The chemistry of the young Earth constantly changed. Hot water reacted with volcanic rocks. Minerals dissolved, separated, and formed new compounds. Gases entered and left the atmosphere. Lightning, sunlight, volcanic heat, and chemical reactions all affected the materials present on the planet. These changing conditions prepared the environment for later stages of Earth's history. The oceans became important places for chemical activity. Water dissolved many substances carried from rocks and volcanoes. Different minerals mixed together under changing temperatures and pressures. Hydrothermal vents on the ocean floor released hot water rich in dissolved minerals. These environments provided many opportunities for complex chemical reactions. Earth's rotation was also different during its earliest history. The young planet spun much faster than it does today. As a result, one day lasted only a few hours. Over billions of years, the gravitational pull between Earth and the Moon gradually slowed Earth's rotation, making days longer. The Moon slowly moved farther away from Earth as time passed. Even today, careful measurements show that the Moon continues moving outward at a very slow rate. This gradual change results from the exchange of energy through tidal interactions between Earth and the Moon. The earliest atmosphere blocked much of the sunlight differently than today's atmosphere. Without free oxygen, there was no ozone layer to absorb much of the sun's ultraviolet radiation. Large amounts of ultraviolet light reached Earth's surface. This radiation affected chemical reactions taking place in the atmosphere and oceans. The early Earth experienced constant volcanic eruptions. Magma rose from deep inside the planet through cracks in the crust. Lava spread across the surface before cooling into solid rock. Volcanic gases continued adding new material to the atmosphere. Ash and volcanic particles sometimes spread across wide regions before settling onto land and into the oceans. Earth's interior became organized into distinct layers because of differences in density and composition. The crust formed the thin outer shell. Beneath it lay the mantle, made mostly of hot, solid rock, capable of flowing slowly over long periods. At the center lay the iron-rich core, divided into liquid and solid regions. Each layer played a different role in the planet's development. Heat moved from Earth's interior toward the surface through several processes. Some heat traveled by conduction through solid rocks. Some moved through flowing material inside the mantle. Volcanoes carried additional heat directly from deep inside the planet to the surface. This continuous movement of heat remains active today. The formation of Earth's oceans also affected the cooling of the crust. Water absorbed and moved heat efficiently. Rain, rivers, and waves slowly broke apart rocks. Tiny pieces of rock collected in low areas, beginning the long history of sediment formation that continues today. Small amounts of the earliest crust still survive within some ancient regions of today's continents. Scientists carefully study these rocks because they contain valuable information about Earth's earliest conditions. Their minerals record temperatures, pressures, and chemical environments from billions of years ago. The birth of Earth was not an isolated event. At nearly the same time, Mercury, Venus, Mars, and the giant planets also formed from the same rotating disk surrounding the young Sun. Although they shared a common beginning, differences in size, distance from the Sun, composition, atmosphere and later geological activity caused each planet to follow its own path of development. Earth's position within the solar system became important because it allowed temperatures suitable for liquid water over long periods. If Earth had formed much closer to the Sun, higher temperatures would have greatly affected the stability of water. If it had formed much farther away, lower temperatures would have changed the planet in different ways. Its location allowed water to remain present across much of the surface after the planet cooled sufficiently. Throughout these earlier stages, every change depended on natural physical processes. Gravity gathered material into larger bodies. Heat melted the interior. Heavy elements moved inward while lighter materials stayed closer to the surface. Volcanoes released gases. Water condensed into oceans. Impacts reshaped the surface. The moon formed from debris after a giant collision. The atmosphere slowly developed through volcanic activity. The magnetic field began protecting the planet. The crust cooled and changed. These events together shaped the young Earth during the earliest chapter of its long history. Earth's earliest history began after the young planet formed from dust, rock, and other materials that surrounded the newborn sun. During this time, Earth was very different from the world that exists today. It did not have blue oceans, green forests, animals, or clean air. Instead, its surface was covered by intense heat. Huge amounts of energy from constant impacts, radioactive elements inside the planet, and the movement of heavy materials toward the center kept Earth extremely hot. The surface was covered by a deep layer of melted rock known as magma. This molten surface stretched across the young planet and changed continuously as fresh material fell from space and mixed with the hot rock below. As time passed, Earth slowly began to lose some of its heat. The process was very slow because the planet was enormous and held a great amount of heat inside. Even though the surface remained very hot for a long time, the outermost layer gradually cooled enough for solid rock to begin forming. This marked the beginning of Earth's first crust. The crust was the thin outer layer of solid rock that covered the molten material underneath. It was not smooth, strong, or stable. It often cracked apart because of the heat below. Large sections melted again as fresh magma reached the surface. Powerful volcanic activity constantly changed the young crust, making it difficult for any single part to remain unchanged for long. The earliest crust probably formed in many different places instead of appearing everywhere at the same time. Some areas cooled faster than others because conditions were slightly different across the planet. When the hot surface cooled enough, minerals inside the magma joined together to create crystals. These crystals became the building blocks of the first solid rocks. As more crystals formed, they connected to produce larger masses of rock. This slow cooling allowed Earth's surface to develop its first solid shell. Scientists believe that much of this earliest crust was made from dark rocks that were rich in iron and magnesium. These rocks were heavier than many rocks that formed later in Earth's history. The first crust was much thinner than the crust found on many continents today. It also broke apart more easily because Earth's interior was still much hotter than it is now. Heat rising from below caused many parts of the crust to crack, sink, melt, and form again. This endless activity meant that very little of the first crust survived into later ages. The oldest rocks that scientists have found today are much younger than Earth itself. This is because the earliest crust was recycled many times. As sections of crust moved, some were pushed back into the hot interior where they melted again. Fresh magma later reached the surface and cooled into new rock. This constant recycling erased much of the evidence from Earth's earliest years. Even though most of the first crust disappeared, tiny mineral crystals known as zircons have survived from that distant time. These small crystals formed inside ancient rocks and remained strong enough to survive many changes. They provide valuable information about conditions on the young planet. Studies of ancient zircons suggest that some parts of Earth's surface had already cooled enough to support solid crust surprisingly early in the planet's history. The chemical makeup of these crystals also suggests that liquid water may already have existed while they were forming. This idea has helped scientists understand that Earth may have become cooler, faster than once believed, although many parts of the planet still remained extremely active. While the crust slowly developed, the inside of Earth continued changing as well. Heavy elements, such as iron and nickel, moved toward the center because of their great weight. This process formed Earth's core. Lighter materials remained closer to the surface and became part of the mantle and crust. The movement of these materials released even more heat, keeping much of the planet active. The separation of materials inside Earth also helped create the structure that still exists today, with a core deep inside, a thick mantle above it, and the thin crust forming the outer surface. Volcanoes played a major role during this early period. They were far more common than they are today. Cracks in the young crust allowed magma to rise easily from deep inside the planet. When this magma reached the surface, it spread across the land as lava. At the same time, volcanoes released enormous amounts of gas into the sky. These gases included water vapor, carbon dioxide, nitrogen, sulfur compounds, hydrogen, and several other gases. The release of gases from Earth's interior is called volcanic outgassing. This process was one of the main ways the young planet gained its early atmosphere. Earth's first atmosphere was very different from the air people breathe today. It did not contain enough oxygen to support human life or most modern living things. Instead, it was filled with gases released by volcanoes and by the materials that helped build the planet. Some scientists also believe that the earliest atmosphere included hydrogen and helium, gathered from the cloud of gas surrounding the young sun. However, these very light gases did not remain around Earth for long. Because the young planet was still very hot and because the solar wind from the active young sun was very powerful, much of the hydrogen and helium escaped into space. After these light gases disappeared, a new atmosphere gradually formed from volcanic gases. Water vapor became one of its most important parts. Carbon dioxide was also present in very large amounts. Nitrogen slowly became one of the most common gases as time passed. Other gases such as methane, ammonia, sulfur dioxide, hydrogen sulfide, carbon monoxide and hydrogen were also present in different amounts. The exact mixture changed over time as volcanic activity continued and chemical reactions took place between the atmosphere, the surface, and the oceans that later formed. The early atmosphere looked very different from today's sky. Thick clouds often covered much of the planet. Dust from volcanic eruptions filled the air. Ash from repeated eruptions spread across large areas before settling back onto the ground. Lightning was likely common because of powerful storms, volcanic eruptions, and the movement of ash particles through the atmosphere. Rain may have fallen frequently once temperatures became low enough, although volcanic eruptions often added more heat and gases back into the air. The absence of free oxygen made Earth's early atmosphere very different from today's environment. Oxygen is highly reactive and easily combines with many other elements. Before living organisms began producing oxygen in large amounts, nearly all available oxygen became locked inside rocks and minerals. Iron combined with oxygen to form iron-rich minerals. Silicon combined with oxygen to produce many common rock-forming minerals. As a result, very little free oxygen remained in the atmosphere. Without an ozone layer, the surface received much stronger ultraviolet radiation from the sun than it does today. Ultraviolet radiation can damage many types of molecules. Because the ozone layer had not yet formed, these rays easily reached the ground and the surface of the oceans. Early life that eventually appeared had to survive under these harsh conditions, often by living underwater or beneath rocks where some protection was available. As volcanic activity continued releasing water vapor into the atmosphere, the amount of moisture in the air increased greatly. During the hottest period, this water remained as vapor because temperatures were too high for liquid water to exist for long on the surface. The atmosphere became thick with steam. Gradually, Earth's surface cooled enough for water vapor to condense into tiny droplets. Clouds became larger and thicker. Rain began falling onto the cooling crust. The first rainfall did not create calm lakes and peaceful rivers immediately. The hot surface caused much of the rain to evaporate again. Water returned to the atmosphere as vapor, only to cool once more and fall again. This repeated cycle continued over a very long period as Earth's temperature slowly decreased. Eventually, some water remained on the surface long enough to collect in low areas. Small pools joined together to form larger bodies of water. These growing bodies of water became the earliest oceans. Their formation marked one of the most important stages in Earth's history, because liquid water became a permanent part of the planet's surface. Water covered many of the lowest parts of the crust. As more rain continued falling, the oceans gradually expanded. Rivers may have carried dissolved minerals from the land into these growing bodies of water, adding different chemical substances to the oceans. Scientists believe that volcanic outgassing supplied much of the water that filled Earth's oceans. Water stored inside minerals deep within the planet escaped through volcanic eruptions as water vapor. Once temperatures became low enough, this vapor condensed into liquid water. Some scientists also think that icy objects from space added extra water by striking Earth during its early history. Small icy bodies and water-rich rocks may have delivered additional water that mixed with the growing oceans. Both sources likely played important roles. The earliest oceans were not exactly like modern oceans. They contained different amounts of dissolved minerals and chemical substances. Continuous volcanic eruptions added many materials to the water. Hot water flowed through cracks in the ocean floor, picking up minerals from underground rocks before returning to the sea. This process changed the chemical makeup of the oceans over time. The water may also have been warmer than today's oceans because Earth still contained much more internal heat. Volcanoes beneath the oceans released heat directly into the surrounding water. Lava flowing onto the ocean floor also warmed nearby areas. Even so, liquid water remained stable across much of the planet because surface temperatures had fallen enough to allow it to exist. The growing oceans influenced Earth's climate in important ways. Water absorbs heat and releases it slowly. As larger oceans formed, they helped spread heat around the planet. Water also became part of the continuous cycle of evaporation, cloud formation, rainfall, and runoff. This water cycle gradually became one of Earth's most important natural systems. Rainwater slowly wore away exposed rocks on the young crust. Tiny pieces of rock broke loose and were carried into streams and oceans. Minerals dissolved into the water through chemical reactions. Carbon dioxide in the atmosphere mixed with rainwater to form weak acids. These weak acids slowly reacted with rocks, removing some carbon dioxide from the atmosphere. These dissolved materials were carried into the oceans, where some later became part of new minerals. The removal of carbon dioxide from the atmosphere slowly changed Earth's climate. Carbon dioxide traps heat, so reducing its amount gradually affected surface temperatures. Some carbon dioxide also became trapped inside minerals and rocks. Over very long periods, these natural processes helped shape the balance between Earth's atmosphere, oceans and crust. The young crust continued changing as heat from the mantle below forced sections to move. Some parts cracked apart while others collided. Magma filled many of these cracks before cooling into fresh rock. New crust formed while older crust disappeared beneath the surface. Although these early movements may not have been exactly the same as modern plate tectonics, they marked the beginning of the processes that later shaped continents and ocean basins. Large volcanic regions were common across the planet. Some volcanoes released lava gently, while others exploded with tremendous force. Ash clouds spread through the atmosphere and settled over wide areas. Layers of volcanic rock built up across the landscape. Repeated eruptions buried older rocks beneath newer ones. This constant rebuilding made Earth's surface one of the most active places in the early solar system. Meteorite impacts also remained common during Earth's early history. Large rocks from space struck the planet with enormous energy. Some impacts melted parts of the crust again. Others blasted huge amounts of rock and dust into the atmosphere. Very large impacts could temporarily heat wide regions and affect the growing atmosphere and oceans. Despite these violent events, Earth continued cooling overall as time passed. The interaction between impacts, volcanic activity, and cooling created a planet that constantly changed. Fresh rock formed, broke apart, melted, and formed again. Water collected, evaporated, and returned as rain. Gases entered the atmosphere through volcanic eruptions, while chemical reactions removed some of them. Every part of the young Earth influenced every other part. The first continents did not appear suddenly. Instead, lighter rocks slowly gathered into larger masses that floated higher on the mantle than the heavier rocks beneath them. Over long periods, these lighter areas became the earliest continental crust. They were smaller than today's continents and changed shape many times through volcanic activity and crustal movement. Granite-rich rocks eventually became more common within these growing continental regions. Granite is lighter than many dark volcanic rocks. Because of this, continental crust became thicker and more stable than much of the earlier crust. These growing land areas remained above sea level more often, allowing rivers and rainfall to shape their surfaces. Hydrothermal systems developed where water reached hot rocks beneath the surface. Water flowed downward through cracks, became heated, dissolved minerals, and returned upward. These hot water systems carried many chemical substances from underground into the oceans. They created environments rich in dissolved minerals and chemical energy. Many scientists think such places may later have provided suitable conditions for some of the earliest forms of life. The atmosphere continued changing as gases reacted with rocks, oceans, sunlight, and each other. Methane and ammonia were broken apart by ultraviolet radiation from the sun. Some chemical reactions produced new substances that entered the oceans or settled onto the surface. Nitrogen gradually became more stable because it reacted less easily than many other gases. Over time, nitrogen became the main gas in the atmosphere. Clouds covered much of the sky during many periods. Water vapor, volcanic ash, and dust affected how sunlight reached the surface. Heavy rainfall likely continued for long stretches, as evaporation and condensation remained active. Storms helped move heat and moisture around the planet, while rivers carried sediment from land into the oceans. The oceans became important places where countless chemical reactions occurred. Minerals dissolved from rocks, mixed with substances, carried by rivers and volcanic activity. Heat from underwater volcanic regions increased chemical activity in many places. Sunlight affected the upper layers of the water, while darkness covered the deepest regions. Different conditions existed throughout the oceans, creating many environments with unique chemical properties. Earth's magnetic field also became important during this early period. The movement of liquid iron inside the outer core generated a magnetic field surrounding the planet. This magnetic field helped reduce the loss of atmospheric gases by deflecting many charged particles coming from the sun. Without this protection, the atmosphere could have been stripped away more quickly by the solar wind. Inside the planet, radioactive elements continued releasing heat as they slowly broke down. This heat contributed to volcanic activity and movement within the mantle. Although radioactive heating became weaker over immense periods, it remained an important source of internal energy throughout Earth's history. The balance between cooling and internal heating shaped the young planet. The surface gradually cooled enough for solid rock and liquid water to remain, while the interior stayed hot enough to drive volcanic eruptions and crustal movement. This balance allowed Earth to develop stable oceans above an active interior. Many minerals that formed during this early time became part of later geological processes. Some rocks were buried deep underground, where heat and pressure changed them into new types of rock. Others remained closer to the surface and were broken apart by weathering. Sediments collected in low areas and later hardened into sedimentary rocks. These different rock types preserved important clues about Earth's earliest environment. Chemical exchanges between the crust, oceans and atmosphere continued without stopping. Volcanoes added gases to the atmosphere. Rain removed some gases and carried them into the oceans. Water dissolved minerals from rocks and transported them across the surface. Some materials settled onto the ocean floor where they became part of new rock layers. Other materials returned to the mantle through crustal recycling. The first crust, oceans and atmosphere were not separate parts of Earth's history. They developed together and influenced one another from the beginning. Cooling allowed crust to form. Volcanoes released gases that built the atmosphere. Water vapor condensed into rain that filled the oceans. Oceans changed the atmosphere through chemical reactions, while also reshaping the crust through weathering and erosion. Internal heat continued driving volcanic activity, which supplied new gases and fresh rock. Throughout these early stages, Earth's surface remained active with constant movement of rock, water, and gases as the young planet continued developing. The early Earth was a very different place from the planet that people know today. Long before animals, forests, flowers, birds, fish, or human beings existed, the planet was covered by wide oceans, rocky land, active volcanoes, and an atmosphere that contained very little free oxygen. The surface continued to change because of heat rising from deep inside the planet. Volcanoes released large amounts of gases into the air, while rain slowly cooled the land and filled the growing oceans. Rivers carried minerals from the rocks into the seas. The oceans became rich in many kinds of simple chemical substances that were mixed together over very long periods of time. Scientists believe that life did not appear suddenly. It developed through many small natural steps that took place across an extremely long period. The first living things were very simple. They were much smaller than anything that could be seen with human eyes alone. They had no bones, no muscles, no leaves, no flowers, no eyes, no brains, and no organs. Even though they were very simple, they were alive because they could grow, take in energy, make copies of themselves, and pass on their basic characteristics to the next generation. The earliest signs of life appeared about 3,800,000,000 years ago. Some scientists believe that life may have started even earlier, although the oldest evidence has changed over time as new discoveries have been made. Rocks from this very ancient time are rare because Earth's surface has been changed again and again by heat, pressure, earthquakes, volcanoes, and the movement of continents. Many of the oldest rocks have been broken apart, melted, buried, or changed into different kinds of rock. This makes it difficult to find clear evidence from the earliest days of life. Scientists search for signs of ancient life by studying very old rocks from different parts of the world. They examine tiny structures inside the rocks, study the chemical makeup of minerals, and look for patterns that living things may have left behind. They also study modern microorganisms to understand how ancient life may have lived. Every new discovery helps scientists build a clearer picture of Earth's earliest living world. Many scientists think that life first appeared in the oceans. Water provided a place where important chemical substances could mix together. The oceans protected tiny living cells from strong sunlight and harmful conditions on the surface. Water also helped carry nutrients from one place to another. Since living cells need water to carry out the chemical activities that keep them alive, the ancient seas offered a suitable environment for the first simple organisms. The exact place where life began is still being studied. Some scientists believe it started near deep, underwater volcanic openings on the ocean floor. These places released hot water filled with minerals from inside the Earth. The hot water mixed with the cold seawater and created areas where many chemical reactions could happen. Tiny openings in the rocks may have trapped important substances close together, allowing more complex chemicals to form over time. Other scientists suggest that life may have begun in shallow pools of water near volcanic regions. Rainwater could collect in these pools, bringing together different chemicals from the surrounding rocks. As the water level changed, the chemicals became more concentrated. Heat from the sun, lightning, and volcanic activity may have provided energy that helped simple chemicals join together into larger and more complex molecules. Scientists have also suggested that life may have started in other watery environments, such as coastal areas, warm springs, or places where fresh water mixed with seawater. Each of these ideas is supported by different kinds of scientific evidence, and researchers continue to investigate which environment was most suitable for the first living cells. Before life appeared, the Earth already contained many of the basic chemical elements needed for living things. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur were present in the oceans, the atmosphere, and the rocks. These elements combined in different ways to form simple molecules. Over very long periods of time, these molecules joined together to create more complex substances. Some of these complex molecules became important parts of the first living cells. Living cells contain large molecules that carry out different jobs. Some help build the structure of the cell, others store energy, some speed up chemical reactions, others carry genetic information that allows living things to make copies of themselves. Scientists believe that these important molecules developed gradually through natural chemical processes before the first true cells appeared. One of the greatest questions in science is how the first cell formed. A living cell is much more than a collection of chemicals. It has a boundary that separates it from the outside world. Inside the cell, many chemical activities happen at the same time. The cell takes in nutrients, removes waste, repairs damage, and makes copies of itself. Scientists continue to study how these abilities first came together in one simple living system. The earliest cells were probably much simpler than modern cells. They likely had only the basic parts needed for survival. They did not have the many special structures found in more advanced cells today. Their main goal was to stay alive long enough to grow and reproduce. Even these simple activities required many carefully organized chemical reactions inside each tiny cell. The first living organisms probably obtained energy from chemicals found in their surroundings. The ancient oceans contained many dissolved substances that could be used during chemical reactions. These early organisms may have absorbed these materials directly through their outer covering. Since they were extremely small, nutrients could easily move into the cells without the need for special organs. As these tiny organisms reproduced, small changes sometimes occurred. These changes happen naturally during the process of making new cells. Some changes made it easier for certain organisms to survive under local conditions. Those organisms produced more offspring, passing these helpful characteristics to future generations. Over many millions of years, these small changes led to greater variety among living organisms. The earliest forms of life were single-celled organisms. Each organism consisted of only one cell that carried out every activity needed for life. Even though each cell was very small, it was able to sense its surroundings, take in food, release waste, grow larger, and divide into new cells. Single-celled life remained the only form of life on Earth for an extremely long period. These early organisms lived in many parts of the oceans. Some floated freely in the water, others settled onto the ocean floor. Some attached themselves to rocks or other solid surfaces. Groups of microorganisms often formed thin layers that covered underwater rocks. These communities slowly grew as new cells divided and remained close together. One important kind of ancient structure formed by these communities is known as a stromatolite. Stromatolites developed when microorganisms trapped tiny particles carried by the water. Layer after layer slowly built up over long periods, creating rounded, rocky structures. Some ancient stromatolites are among the oldest widely accepted evidence of life on Earth. Similar structures can still be found in a few places today, showing how this very old way of life has survived for an extremely long time. The microorganisms that formed stromatolites often lived in large groups. Each individual cell carried out its own activities, yet together they created structures that lasted for thousands of years. These rocky formations recorded the presence of living organisms in places where soft cells would normally disappear after death. Most of the earliest living organisms were bacteria or organisms closely related to bacteria. Modern bacteria exist in almost every environment on Earth, from deep underground to high mountains, from hot springs to frozen regions, and from ocean floors to the human body. This wide range of habitats suggests that their ancient ancestors were also highly adaptable. Scientists divide these ancient microorganisms into different groups based on their cell structure and genetic material. Two major groups are bacteria and archaea. Both groups are made of single cells, but they differ in important ways. Studies of their genes show that they separated from each other very early in the history of life. Archaea often live in places with very high temperatures, high salt levels, or other difficult conditions, although many also live in ordinary environments. The ability of these simple organisms to survive under many different conditions allowed life to spread across much of the planet. As more environments became suitable for life, microorganisms occupied them and continued reproducing. Their populations slowly increased, filling the ancient oceans with countless tiny living cells. The early atmosphere contained very little free oxygen. Because of this, many ancient microorganisms lived without using oxygen during their chemical activities. Modern scientists call these organisms anaerobic organisms because they do not depend on oxygen for survival. Some modern microorganisms still live in this way, giving researchers valuable information about conditions on the early Earth. The first living organisms played an important part in changing the planet itself. As they carried out their daily activities, they changed the chemistry of the water around them. Over long periods, the combined effect of countless microorganisms slowly influenced the oceans and the atmosphere. Later groups of microorganisms developed the ability to use sunlight as their energy source. This important step would eventually increase the amount of oxygen in the atmosphere, although that change happened much later and required an extremely long period of time. The development of photosynthesis marked a major event in the history of life. During photosynthesis, certain microorganisms captured energy from sunlight and used it to produce food. As part of this process, oxygen was released into the surrounding water. At first, this oxygen reacted with dissolved iron and other substances, instead of remaining in the atmosphere. Only after these materials became filled with oxygen did free oxygen begin to build up in the oceans and later in the air. The appearance of oxygen slowly changed Earth's environment. Many early organisms that could not survive in oxygen-rich conditions disappeared from places where oxygen levels increased, while others continued living in areas where oxygen remained low. New forms of life that could use oxygen gradually developed, opening the way for greater biological diversity. The early oceans were home to countless invisible living cells that carried out simple but essential activities every day. They divided, spread into new areas, absorbed nutrients, repaired damage, and continued the long process of biological change that shaped every later form of life. The Great Oxygen Revolution was one of the most important events in the long history of Earth. It changed the air, the oceans, the land, and the future of life. Before this event, the world was very different from the planet we know today. The air did not contain much oxygen. Most living things that existed during that time did not need oxygen to survive. They lived in oceans where they found energy from simple chemical reactions and from the conditions around them. The land was empty and lifeless. There were no forests, no animals, and no people. The sky also looked different, because the gases in the air were not the same as they are today. During the earliest part of Earth's history, the planet had already formed its solid surface, its oceans, and its first simple forms of life. The first living organisms were very small. They were made of only one cell. These tiny organisms lived in the oceans because water protected them from the strong sunlight that reached Earth's surface. At that time, the sun sent large amounts of harmful radiation toward Earth because there was no protective ozone layer high in the atmosphere. Life remained in the water where it had a better chance to survive. The atmosphere of early Earth was made of gases, released by volcanoes and by the young planet itself. These gases included carbon dioxide, methane, water vapor, nitrogen, hydrogen sulfide, and several others. Oxygen was almost completely absent. If a person from today could travel back to that time, breathing the air would not be possible. Human life depends on oxygen, but the early atmosphere could not support it. The oceans covered much of Earth's surface. They contained many dissolved minerals that washed into the water from rocks and volcanic activity. One of the most common dissolved materials was iron. Huge amounts of iron floated through the ancient seas because there was almost no oxygen to react with it. The water often looked different from modern oceans because of the large amount of dissolved iron and other chemicals. The earliest living organisms found ways to survive in this unusual world. Some received energy from chemicals that came from deep inside Earth. Others slowly developed new ways to gather energy. One group of tiny organisms eventually discovered a method that would completely change the history of the planet. These organisms were called cyanobacteria. They were simple living cells that lived mostly in shallow oceans, where sunlight could easily reach them. Cyanobacteria developed the ability to use sunlight as a source of energy. They took in carbon dioxide from the surrounding water and used sunlight to help produce food inside their cells. During this process, they also used water. As they completed this natural process, they released oxygen as a waste product. This process is known today as photosynthesis. At first, this new ability may not have seemed important because the amount of oxygen released into the environment was very small. The first cyanobacteria spread through many shallow seas. They formed large groups that covered wide areas of the ocean floor. Some of these groups created layered structures known today as stromatolites. These structures formed as the tiny cells trapped particles and continued growing layer after layer over long periods of time. Many ancient stromatolites have survived as fossils, giving scientists important evidence of early life and the beginning of oxygen production. For a very long time, the oxygen released by cyanobacteria did not remain in the atmosphere. Instead, it quickly reacted with other materials around it. Oxygen is a very active gas. It easily combines with many different substances. One of the first materials it reacted with was the large amount of dissolved iron in the oceans. As oxygen met iron, the two joined together to form iron oxide. These solid particles slowly sank to the bottom of the sea. Over countless generations, layer after layer of iron oxide settled on the ocean floor. These layers mixed with other sediments and slowly became solid rock. Today, these rocks are known as banded iron formations. They are found in many parts of the world and serve as strong evidence that oxygen was beginning to appear in Earth's oceans. These ancient rocks are also important sources of iron used in modern industry. For a very long period, nearly all the oxygen produced by cyanobacteria was used up by reactions with iron and other chemicals. As long as these materials remained available, oxygen could not build up in large amounts in the atmosphere. The oceans acted as a place where oxygen was constantly removed through natural chemical reactions. Eventually, much of the dissolved iron had already combined with oxygen. Many other materials that reacted easily with oxygen had also become less common. As this happened, the oxygen produced by cyanobacteria could finally begin to collect in seawater and later enter the atmosphere. This marked the beginning of a major change in Earth's environment. As more oxygen entered the atmosphere, the air slowly changed. The increase happened over an extremely long period. It was not a sudden event that happened in a short time. Generation after generation of cyanobacteria continued producing oxygen every day. Their work slowly changed the chemical makeup of the entire planet. This change took place around 2,400,000,000 years ago. Scientists call this event the Great Oxygen Revolution, or the Great Oxidation Event. It marked the first time that oxygen became an important part of Earth's atmosphere. Although the amount of oxygen was still much lower than today, the increase was enough to change many natural processes across the planet. The arrival of oxygen created serious problems for many living organisms that had evolved in an environment without it. Many of these early organisms could not survive when exposed to oxygen because it damaged important parts of their cells. For them, oxygen acted as a harmful substance. As oxygen levels increased, many of these organisms disappeared from areas where oxygen became common. Some of these organisms survived by moving into places where oxygen remained very low. They found shelter deep underground, inside rocks, beneath the ocean floor, and in other places where oxygen could not easily reach. Even today, some living organisms continue to survive in environments that contain little or no oxygen, showing that these ancient forms of life never completely disappeared. At the same time, other living organisms slowly developed ways to use oxygen instead of avoiding it. Using oxygen allowed cells to release much more energy from food than older methods. This extra energy helped support more active and more complex forms of life. Over many millions of years, this change opened new possibilities for biological development. As oxygen continued to rise, another important change happened high above Earth's surface. Some oxygen molecules were changed by sunlight into ozone. Ozone formed a layer high in the atmosphere that absorbed much of the harmful ultraviolet radiation coming from the sun. Before this protective layer existed, strong radiation reached Earth's surface with little resistance. The new ozone layer reduced the amount of dangerous radiation reaching the ground and the upper parts of the oceans. The development of the ozone layer made Earth's surface safer for living organisms. Life still remained mostly in the oceans for a long time, but conditions on land slowly became less dangerous. Much later, plants, fungi, and animals would eventually spread across the continents because the harmful radiation had become much weaker than before. The Great Oxygen Revolution also affected Earth's climate. Methane was one of the important gases in the early atmosphere. Methane helped keep the young planet warm because it trapped heat. As oxygen increased, it reacted with methane and reduced the amount of methane in the atmosphere. With less methane available, Earth's climate became cooler. Scientists believe this cooling may have contributed to long periods when large amounts of ice covered parts of the planet. These cold periods changed the environment for many living organisms. Life had to adjust to lower temperatures and changing conditions. Some organisms disappeared while others survived by adapting to their surroundings. The history of life has always included changes in response to changing environments. The increase in oxygen also changed the chemistry of the oceans. Many chemical reactions that had been common for millions of years became less common as oxygen spread through seawater. New minerals formed. Old chemical cycles changed. The balance of many substances in the oceans slowly shifted as oxygen became part of the environment. Cyanobacteria continued producing oxygen throughout these changes. They remained successful because sunlight, water, and carbon dioxide were widely available. Their simple process continued every day across countless generations. Even today, cyanobacteria still exist in lakes, rivers, oceans, and moist environments around the world. They continue carrying out photosynthesis just as their ancient ancestors did long ago. The story of the Great Oxygen Revolution also explains why oxygen is closely connected to plants today. Modern plants use the same basic process that cyanobacteria developed billions of years ago. Plants take in carbon dioxide, use sunlight to produce food, and release oxygen into the atmosphere. This process continues to support life across the planet every day. The rise of oxygen made it possible for more complex cells to appear. These cells contained specialized structures that helped them carry out different tasks more efficiently. One of these structures became known as the mitochondrion. Mitochondria use oxygen to release energy from food inside cells. This process provides much larger amounts of energy than earlier methods used by simple organisms. The greater supply of energy supported the development of larger cells and eventually groups of cells working together. Over vast stretches of time, living things slowly became more complex. New forms of life appeared, each building upon the biological changes that had taken place over many millions of years. The Great Oxygen Revolution did not affect only living organisms. It also changed rocks, soil, water, and the atmosphere. Oxygen reacted with minerals exposed at Earth's surface. Many rocks developed new colors because iron inside them combined with oxygen. Red, brown, and orange colors found in many rocks today are often the result of this natural process. The atmosphere continued changing over long periods as oxygen slowly increased. The balance of gases gradually became more suitable for the development of later forms of life. Nitrogen remained the largest part of the atmosphere, while oxygen slowly became the second largest gas. Around 2,100,000,000 years ago, life on Earth entered a very important stage. For a very long time before this period, the only living things on Earth were simple cells. These tiny living things had no nucleus and no special parts inside their bodies that carried out different jobs. They lived in the oceans and slowly spread across many places. They changed little over long periods because simple life grows and changes very slowly. Even though these tiny cells looked simple, they were active. They found food, reproduced, repaired themselves, and adapted to many different conditions. Over countless generations, they slowly changed through natural processes. Small changes built up over a very long time and prepared the way for a completely new kind of living cell. Earth itself also continued to change during this time. The atmosphere held much more oxygen than it had in earlier ages. This oxygen had been produced by tiny organisms called cyanobacteria. These organisms lived in shallow seas where sunlight reached the water. They used sunlight to make food and released oxygen as a waste product. At first, much of this oxygen reacted with iron and other materials in the oceans and rocks. After these materials could no longer absorb large amounts of oxygen, the gas began to build up in the atmosphere. This slow increase happened over hundreds of millions of years. The growing amount of oxygen changed the conditions in the oceans and the air. Many simple organisms that could not survive in oxygen-rich surroundings disappeared from places where oxygen became common. Other organisms slowly developed ways to live with oxygen. Some even learned how to use oxygen to release much more energy from the food they ate. This gave them a better supply of energy for growth, repair, and reproduction. More energy also allowed cells to become larger and carry out more activities than before. The appearance of complex cells marked one of the greatest events in the history of life. These new cells are known today as eukaryotic cells. Unlike the older simple cells, complex cells had a nucleus. The nucleus held the cell's genetic material inside a protective covering. This helped organize the instructions needed for life. Instead of having genetic material floating freely inside the cell, the information stayed safely inside the nucleus, where it could be copied and passed to new cells with greater accuracy. Complex cells also contained many tiny structures inside them. Each structure had a different job. Some produced energy, some helped make proteins, others stored materials or moved substances from one place to another. This division of work made the cells much more organized. Each part carried out its own task while working together with the rest of the cell. This made the whole cell more efficient and allowed it to perform activities that simple cells could not perform. Scientists believe that one of the most important events in the rise of complex cells happened when one simple cell entered another cell without being destroyed. Instead of acting as enemies, the two cells continued living together. Over many generations, this partnership became permanent. The smaller cell provided energy for the larger one, while the larger cell gave the smaller one protection and food. After a very long time, the smaller cell changed into a part of the larger cell. Today, this part is known as the mitochondrion. Almost every complex cell uses mitochondria to produce energy. Mitochondria are often described as the energy producers of complex cells because they help release energy from food using oxygen. This process gives cells much more usable energy than older methods used by simple cells. The extra energy supports larger cell size, faster growth, better repair, and more complicated activities. Mitochondria still carry a small amount of their own genetic material, which supports the idea that they were once free-living organisms long ago. Some complex cells later formed another partnership with a different kind of simple organism. This second partner was able to use sunlight to make food. Over many generations, it also became a permanent part of the larger cell. These structures became chloroplasts. Chloroplasts are found in algae and plants today. Like mitochondria, chloroplasts also contain their own genetic material. This provides another important clue about their ancient history. The appearance of chloroplasts allowed certain complex cells to produce their own food using sunlight, water, and carbon dioxide. These cells released oxygen into the water and the atmosphere. As more of these organisms spread through the oceans, they added even more oxygen to Earth's environment. This helped create better conditions for many forms of life that depended on oxygen. Complex cells became more common in the oceans over millions of years. At first, they were still single-celled organisms. Even though they consisted of only one cell, they showed many different shapes and ways of life. Some floated freely in the water, others stayed attached to rocks or the seafloor. Some hunted smaller organisms, others absorbed nutrients directly from the surrounding water. Many reproduced by dividing into two cells, while others developed more complex methods of reproduction. The inside of a complex cell became a busy place where many activities happened at the same time. The nucleus controlled the use of genetic information. Mitochondria supplied energy. Tiny structures called ribosomes produced proteins. Other structures helped package and move materials throughout the cell. Membranes separated different activities so that each process could happen under the best conditions. This organization allowed complex cells to carry out many tasks without interfering with one another. The genetic material inside complex cells became more organized than in earlier life forms. Long strands of genetic information were packed into structures called chromosomes. During reproduction, these chromosomes could be copied and passed on carefully to new cells. Small changes sometimes appeared in the genetic material. Some changes had little effect, while others gave organisms new features that helped them survive under changing conditions. One important development in many complex organisms was sexual reproduction. Instead of producing new individuals from only one parent, two parents contributed genetic material to their offspring. This mixed the genetic information in new ways. Every new generation contained many different combinations of inherited traits. Some of these traits improved the chances of survival and reproduction. This increased the variety found within populations over very long periods. Greater genetic variety gave life more opportunities to adapt to changing environments. Conditions on Earth continued to change because of movement of continents, changes in climate, volcanic activity, and shifts in ocean chemistry. Organisms with helpful inherited traits were more likely to survive and reproduce. Their descendants carried these useful traits into future generations. Over millions of years, this process slowly produced new kinds of living things. Some complex cells began living together in groups. At first, these groups may have formed only for short periods. Later, some groups remained together after reproduction. Cells started sharing work among themselves. Certain cells became better at gathering food. Others became better at movement or protection. This sharing of jobs increased the chances of survival for the whole group. Living together required cells to communicate with one another. They developed chemical signals that allowed them to exchange information. These signals helped cells know when to grow, divide, repair damage, or respond to changes in their surroundings. Good communication allowed groups of cells to function as a single living body, rather than as many separate individuals. Over long periods, these groups became more closely connected. Cells depended on one another for survival. Individual cells could no longer live successfully by themselves because each one carried out only certain jobs. This marked the beginning of multicellular life. Many cells joined together to create one organism. Each cell remained alive, but all worked for the benefit of the entire body. The earliest multicellular organisms were simple in structure. They probably lived in the oceans where water supported their bodies and carried nutrients to them. Some attached themselves to the seafloor. Others floated in the water or moved very slowly across soft ocean sediments. These early organisms had no hard skeletons, no shells, and no complex organs. Their soft bodies rarely became fossils, because soft tissues usually decay before they can be preserved. Even though these first multicellular organisms looked simple, they represented another major step in the history of life. Different cells inside their bodies carried out different jobs. Some helped collect food, others provided support, some handled reproduction. This division of work allowed the whole organism to survive more successfully than a collection of separate cells acting independently. The oceans during this time contained many kinds of tiny living organisms. Single-celled algae became common in many shallow waters where sunlight reached easily. These algae produced food through photosynthesis and released oxygen. Tiny animals fed on algae and other microscopic life. Simple food chains slowly developed in many marine environments. Each organism depended on the availability of food, suitable water conditions, and successful reproduction. The seafloor provided many places where early organisms could settle. Mud, sand, and rocky surfaces supported different forms of life. Bacteria continued breaking down dead material and returning nutrients to the environment. These nutrients became available for other living things. This steady movement of nutrients helped support growing populations of organisms throughout the oceans. Over time, the number of different complex organisms slowly increased. New body forms appeared through gradual changes passed from one generation to the next. Some organisms developed outer coverings that offered protection. Others developed better ways of gathering food or attaching themselves to surfaces. Every small change that improved survival could spread through future generations if it increased the chances of successful reproduction. The history of life on Earth began with very small living things that had only one cell. These simple forms of life lived for a very long time before larger and more complex living things appeared. The change from single-celled life to multicellular life was one of the most important events in the history of Earth. It allowed living things to grow larger, develop different body parts, and carry out many activities that a single cell could not perform alone. The first multicellular life did not appear suddenly. It developed through a very long period as simple cells slowly changed over many millions of years. These changes happened little by little through natural processes. As generations passed, some groups of cells began living together instead of separating after they divided. Over time, these groups became more organized and more successful at surviving. Long before animals, plants, and fungi appeared in the forms that are familiar today, Earth was home to tiny living cells that filled the oceans. These early living things depended on water, because it provided protection, nutrients, and a stable place for life to continue. The oceans covered much of the planet, and they became the home of nearly all early life. Inside these waters, single-celled organisms grew, divided, and spread into many different environments. Some floated near the surface where sunlight reached the water, while others lived in deeper places where sunlight could not enter. Different kinds of cells slowly developed different ways of getting energy. Some used sunlight, while others depended on chemicals found in the water. As these simple forms of life continued to exist, Earth's atmosphere also changed. Very early in Earth's history, there was almost no free oxygen in the air or oceans. Many early organisms lived without oxygen, because they had evolved in conditions where oxygen was not available. Later, tiny organisms that could use sunlight released oxygen into the oceans and atmosphere. This slow increase in oxygen changed many parts of the planet. Some living things could not survive these changes, while others developed ways to use oxygen to produce energy more efficiently. The increasing amount of oxygen made it possible for cells to support more activities and produce more energy than before. This greater supply of energy became one of the important conditions that supported the development of multicellular life. Inside many early cells, important changes were also taking place. Some cells formed close relationships with other smaller cells. Instead of destroying them, they kept them alive inside their bodies. Over many generations, these smaller cells became permanent parts of the larger cells. They performed special jobs that helped the larger cells survive. Some became the structures that produced energy, while others became the structures that carried out photosynthesis in certain groups of organisms. These changes created more advanced cells, known today as eukaryotic cells. These cells were larger, more organized, and able to perform many different activities inside one cell. Eukaryotic cells contained a nucleus that stored their genetic material. They also had many small structures that carried out different tasks. Each part had its own job inside the cell. This organization allowed the cells to become more efficient and better able to respond to changes in their surroundings. These advanced cells eventually became the ancestors of animals, plants, fungi, and many other groups of living things. Before any large multicellular organisms appeared, these eukaryotic cells spent a very long time developing new abilities and spreading across the oceans. Scientists believe that the first steps toward multicellular life may have begun when cells stayed attached after dividing. Normally, one cell divides into two separate cells that move away from each other. Sometimes, however, the new cells remained connected. At first, this may have happened by chance, but in some situations, staying together provided advantages. Groups of connected cells could become larger than single cells. They could collect more food, move differently, or protect themselves more effectively from dangers in the water. These early groups of cells were still very simple. Every cell often looked almost the same and carried out similar activities. If one cell became damaged, the others continued living. Over many generations, natural selection favored groups that worked together successfully. Small changes in their genetic material allowed some groups to become more organized than others. As these useful changes accumulated, different cells within the same group slowly began performing different jobs. Cell specialization became one of the greatest developments in the history of life. Instead of every cell doing every task, some cells became responsible for one activity while others carried out different duties. Some focused on collecting nutrients, others helped with movement, some became responsible for reproduction. This sharing of work allowed multicellular organisms to become larger and more efficient. Each cell no longer needed to perform every possible task because neighboring cells provided support. Communication between cells also became very important. Cells needed ways to send signals to one another so they could work together. They developed chemical messages that allowed them to coordinate their activities. When one group of cells detected changes in the environment, it could send signals to other cells. These signals helped the entire organism respond as one unit instead of acting as many separate cells. This ability to communicate became more advanced over long periods of time and formed the basis for increasingly complex bodies. Cells also developed stronger ways of attaching to each other. Special molecules formed connections between neighboring cells and held them together. These connections allowed groups of cells to remain stable even when water currents moved around them. Other substances formed supportive layers outside the cells, giving the organisms additional strength. These developments made it possible for multicellular organisms to maintain their shapes while continuing to grow. The earliest multicellular organisms were very small. Many could not be seen without powerful microscopes if they were alive today. Their bodies contained only a limited number of cells. They had no heads, arms, legs, eyes, or internal organs. They simply existed as small groups of connected cells performing basic life activities. Even though they were simple, they represented a major step forward because they showed that cells could cooperate as members of one living body. Scientists study rocks that formed in ancient oceans to understand these early organisms. Fossils provide valuable evidence about the appearance of early multicellular life. Some fossils preserve the shapes left behind by soft-bodied organisms. Others contain chemical signs that indicate living things once existed in those places. Ancient rocks from different parts of the world contain traces of early multicellular organisms that lived hundreds of millions of years before the appearance of many familiar animal groups. The fossil record for these early organisms is not complete because soft bodies do not fossilize easily. Unlike animals with hard shells or bones, early multicellular organisms were made almost entirely of soft tissues. After they died, their bodies usually broke down quickly. Only under special conditions could their shapes become preserved in mud or fine sediments. Over time, these sediments hardened into rock, protecting the remains for future discovery. Many scientists have spent many years searching ancient rocks for signs of these early forms of life. They carefully study the layers of rock, the minerals they contain, and the chemical signals left behind by ancient organisms. Modern technology allows researchers to examine fossils in great detail. Powerful microscopes, chemical studies, and imaging methods reveal information that earlier scientists could not observe. Every new discovery helps build a clearer picture of how multicellular life first appeared. One important group of early multicellular organisms consisted of simple algae. These organisms used sunlight to produce food through photosynthesis. Some algae existed as single cells, while others formed chains, sheets, or larger bodies made of many connected cells. These multicellular algae showed that groups of cells could work together successfully. Different kinds of algae spread through shallow coastal waters where sunlight was available. They became important producers of food and oxygen in ancient oceans. As multicellular algae expanded, They also provided new places for other organisms to live. Tiny living things attached themselves to the surfaces of algae or lived among their branches. This increased the variety of life within the oceans. Different organisms occupied different parts of the same environment, creating more opportunities for life to continue developing. Some early multicellular organisms reproduced by releasing special reproductive cells into the surrounding water. These cells drifted through the oceans until they met other reproductive cells. After joining together, they developed into new organisms. Other organisms reproduced by breaking into pieces. Each piece contained enough living cells to continue growing into another complete organism. These methods helped multicellular life spread across many parts of the ancient seas. Genetic changes continued to occur in every generation. Most changes had little effect, but some improved survival. Organisms with useful changes often produced more offspring. These successful traits slowly became more common within populations. Over extremely long periods, many small genetic changes produced greater differences between groups of organisms. New forms of multicellular life gradually appeared through this ongoing process. The environment also influenced the development of multicellular organisms. Ocean temperatures changed over long periods. Sea levels rose and fell. Continents slowly moved across Earth's surface. Volcanic activity released minerals into the oceans. Ice ages affected global conditions. Each environmental change created new challenges that organisms needed to survive. Some groups disappeared while others adapted to changing conditions and continued evolving. Food sources influenced how multicellular organisms developed. Some absorbed nutrients directly from the surrounding water. Others captured tiny particles floating in the oceans. Different feeding methods encouraged different body shapes and different ways of growing. As organisms became more specialized, greater diversity appeared among early multicellular life. One of the most remarkable developments was the gradual formation of body plans. Instead of random collections of cells, organisms began growing according to instructions stored in their genetic material. Cells divided in regular patterns and moved into specific positions. This allowed bodies to develop consistent shapes from one generation to the next. Although these early body plans remained simple, they laid the foundation for the much greater complexity that would appear later in Earth's history. Around 541 million years ago, Earth entered a very important period in its long history. This period is known as the Cambrian period. During this time, life in the oceans changed in many ways. Before this period, living things were present on Earth, but most of them were small, soft-bodied and simple in their structure. Many lived quietly on the seafloor or floated in the water. Their bodies did not have hard shells, strong outer coverings or solid skeletons. They were very different from many of the animals that appeared later. During the Cambrian period, many new kinds of living things appeared within a relatively short part of Earth's history. Scientists call this event the Cambrian explosion, because of the large increase in the number and variety of animal life found in rocks from this period. It was not a sudden event that happened in a single moment. It took place over millions of years, but it was much faster than many earlier changes in the history of life. The world during the Cambrian period looked very different from the world today. The continents were not in their present places. Many land areas were gathered into smaller pieces that were spread across different parts of the planet. Large parts of these continents were covered by shallow seas. These warm and sunlit waters became excellent places for life to grow. The shallow seas received sunlight that allowed tiny living things to make food through photosynthesis. This created a rich source of food that supported many different forms of marine life. At this time, there were no forests, grasslands, flowering plants, birds, mammals, or humans. The land was mostly bare rock, sand and soil. Almost all living things existed in the oceans. The sea became the center of life on Earth. Countless living things drifted, crawled, burrowed, swam, and rested on the seafloor. Every part of the ocean began to support different kinds of animals. The oceans contained many tiny organisms that floated freely in the water. These small living things formed the base of the food supply. Tiny algae and other simple organisms used sunlight to make food. Small animals fed on them. Larger animals then fed on those smaller creatures. Food chains became more detailed as new kinds of animals appeared. Different species found different ways to survive. Some collected tiny food particles from the water. Some searched the seafloor for food, others hunted living prey. One important reason for the growth of marine life was the increase in oxygen. During earlier times, tiny organisms had slowly released oxygen into the atmosphere and oceans through photosynthesis. Over a very long time, oxygen levels increased enough to support larger and more active animals. Oxygen helped living things produce energy inside their cells. This allowed animals to grow larger bodies, move more actively, and develop more complex organs. Another important change involved the development of hard body parts. Before the Cambrian period, many animals had soft bodies that were easily damaged after death. Their remains rarely became fossils because soft tissue usually decayed before it could be buried. During the Cambrian period, many animals developed shells, hard outer coverings, spines, or mineralized body parts. These hard structures protected them from danger and also gave support to their bodies. Because these hard parts were stronger than soft tissue, they were more likely to become fossils after burial in mud or sand. This is one reason why rocks from the Cambrian period contain many fossils that help scientists understand early animal life. Many different body designs appeared during this time. Some animals had long bodies divided into many sections. Others had rounded shapes or flattened forms. Some had many legs for crawling across the seafloor. Others developed fins or body parts that helped them swim through the water. Eyes became more common in many groups of animals. Better eyesight allowed animals to find food, avoid danger, and move through their surroundings more effectively. One of the most famous animals from the Cambrian period was the trilobite. Trilobites were marine animals with hard outer shells divided into 3 lengthwise sections. Their bodies were also divided into many segments. They lived in oceans all around the world and became one of the most successful groups of early animals. Many trilobites crawled across the seafloor, searching for food. Some dug into soft mud, while others may have swum for short distances. Different species lived in different environments. Some preferred shallow water, while others lived in deeper parts of the sea. Trilobites had well-developed eyes made of many small lenses. These eyes helped them detect movement and changes in light. Their bodies were protected by hard shells that reduced injuries from attacks or rough conditions. When threatened, many trilobites could roll their bodies into a tight shape that protected their softer parts. This ability helped some species survive in dangerous environments. Another important group of Cambrian animals included brachiopods. These animals had 2 shells that covered their soft bodies. They looked somewhat like clams, but they belonged to a different group of animals. Brachiopods attached themselves to the seafloor or rested on it. They fed by filtering tiny food particles from the water. Water entered their shells, passed over feeding structures inside, and left through another opening. This simple feeding method allowed many brachiopods to live together in large numbers. Sponges were also common in Cambrian seas. These simple animals had bodies filled with tiny holes. Water constantly flowed through these openings. As water moved through the sponge, tiny food particles became trapped inside. Sponges remained attached to rocks or the seafloor throughout their lives. They played an important role in cleaning water and creating places where small organisms could live. Early jellyfish and animals related to them also lived in Cambrian oceans. Their soft bodies rarely became fossils, but a few remarkable fossil sites have preserved their remains. These animals drifted through the water and captured small prey using tentacles equipped with tiny, stinging cells. They added another layer to the growing food web in the sea. Worm-like animals became more common during this period. Some crawled across the seafloor, while others dug tunnels into soft sediment. Burrowing changed the nature of the seafloor. As worms moved through mud and sand, they mixed different layers together. This movement allowed oxygen-rich water to reach deeper into the sediment. Other organisms benefited from these changes because they could live in places that had become richer in oxygen. Many early mollusks also appeared during the Cambrian period. Some had simple shells that protected their bodies. They moved slowly across rocks and mud while feeding on tiny living things or organic material. These early mollusks later gave rise to many different groups that became important throughout Earth's history. The Cambrian oceans also contained strange animals that do not closely resemble most living animals today. One of these was Anomalocaris. It was among the largest predators of its time. Its body was long and flexible. It had large eyes that helped it detect prey in the water. It used special grasping limbs near its mouth to catch food. Its circular mouth contained hard plates that helped break apart prey before swallowing it. Anomalocaris showed that active hunting had already become an important part of ocean life. The appearance of predators changed the lives of many other animals. Species that had once lived without many dangers now faced animals that hunted them. As a result, many developed stronger shells, protective spines, thicker outer coverings, or better movement. Some learned to burrow more deeply into the seafloor. Others stayed hidden beneath rocks or inside small spaces. These changes increased the variety of body forms found during the Cambrian period. Scientists believe that changes in genes also played an important role during this period. Genes control how living things grow and develop. Small changes in important developmental genes may have allowed many new body plans to appear. Different groups of animals developed different arrangements of body parts, including heads, mouths, eyes, legs, and internal organs. These new designs allowed animals to live in many different environments within the oceans. Fossils from Cambrian rocks have been found on every continent. These fossils help scientists understand how life spread across ancient seas. One of the most famous fossil sites is the Burgess Shale in what is now Canada. Another important fossil site is Chengjiang in what is now China. These locations contain many exceptionally preserved fossils, including animals with soft body parts that usually do not survive the fossilization process. Because of these discoveries, scientists have learned a great deal about the appearance and lifestyles of Cambrian animals. The Burgess Shale contains fossils of many unusual animals with detailed preservation. Soft tissues, digestive systems, limbs, and other delicate structures remained preserved because the animals were buried very quickly by underwater mud. The lack of oxygen in the buried sediment slowed decay and allowed exceptional fossils to form. These fossils provide valuable information about early marine ecosystems and the wide variety of life that existed during the Cambrian period. The Chengjiang fossil beds are even older than the Burgess Shale. They preserve many early animals that lived near the beginning of the Cambrian period. Fossils from this site include early vertebrate relatives, arthropods, worms, sponges, and many other marine organisms. These discoveries continue to help scientists study the early history of complex animal life. The Cambrian seas supported many different habitats. Rocky areas provided firm surfaces where animals could attach themselves. Sandy bottoms allowed burrowing animals to dig tunnels. Muddy seafloors supported filter feeders and scavengers. Open water contained swimming animals that searched for food or escaped from predators. Different species occupied different parts of these environments, allowing many forms of life to exist at the same time. The greatest mass extinction in Earth's history happened during the end of the Permian period. It is known as the largest extinction event ever discovered in the long history of life on Earth. Scientists believe it took place about 252 million years ago. During this time, almost every part of the planet experienced major changes. The land, the oceans, and the atmosphere all went through conditions that became very difficult for living things. Many plants and animals that had lived successfully for a very long time disappeared forever. This event changed the history of life and opened the way for new groups of living things to appear later. Before this extinction happened, the Earth looked very different from today. Almost all the land on the planet was joined together into one huge landmass called Pangaea. Because the land was connected, the climate across many areas became dry. Large deserts covered many regions. Rainfall was lower in some places, while other areas experienced seasonal weather that could become very hot during the day and much cooler at night. Coastal areas existed around the edges of the great landmass, but many places were far from the sea. The oceans also looked different. Ocean currents moved in different ways because of the shape of the continents. These conditions affected the movement of heat, water, and nutrients across the planet. Life during the Permian period was rich and varied. Forests covered many areas of land. Different kinds of trees, ferns, seed plants, and other early plants provided food and shelter for many animals. Insects were common and had already become an important part of the natural world. Some insects lived in the soil, while others fed on plants or hunted smaller creatures. Rivers, lakes, and wetlands supported many forms of life. Many kinds of animals lived on land. There were reptiles that came in different shapes and sizes. Some were meat-eaters, while others fed on plants. There were also mammal-like reptiles, which were a group of animals that shared some features with later mammals. These animals had spread across different environments and filled many roles in nature. Some were large and powerful, while others were small and active. Many species had become well adapted to the places where they lived after millions of years of change. The oceans were also full of life. Coral reefs supported many sea animals. Different kinds of shellfish covered the sea floor. Trilobites, which had already lived for hundreds of millions of years, were still present. Brachiopods were among the most common animals in the sea. Crinoids, sea lilies, ammonoids, and many kinds of fish were found in different ocean environments. Tiny living things floating in the water formed the base of many food chains. Large predators hunted smaller animals, while many creatures fed on plants, tiny organisms, or dead material. For many millions of years, life continued to change slowly through natural processes. Species appeared, spread into new areas, and sometimes disappeared. Extinction was already a normal part of Earth's history, but the event at the end of the Permian period was much larger than the ordinary loss of species. It affected almost every environment and almost every group of living things. Scientists have spent many years trying to understand what caused such a massive extinction. They have studied rocks, fossils, ancient minerals, and chemical signs left inside the Earth. These studies suggest that the extinction was not caused by one small event. Instead, many serious changes happened close together over a long period. These changes placed great pressure on living things until many species could no longer survive. One of the strongest ideas supported by scientific evidence is that enormous volcanic eruptions took place in an area that is now part of northern Asia. This region is known today as the Siberian Traps. The eruptions were among the largest known volcanic events in Earth's history. Instead of lasting for only a short time, they continued for many thousands of years. Huge amounts of lava poured onto the surface. Layer after layer of melted rock spread across the land and later hardened into thick rock formations that still exist today. The volcanic eruptions released very large amounts of gases into the atmosphere. One of these gases was carbon dioxide. Carbon dioxide naturally exists in the atmosphere, but when too much is added over a long period, it can trap more heat around the Earth. Scientists believe that the large amount of carbon dioxide released during these eruptions caused the planet to become much warmer. Temperatures increased across both land and sea. Many living things were unable to survive under these warmer conditions. Another gas released by volcanic activity was sulfur dioxide. This gas could mix with water in the atmosphere and form acid rain. Acid rain can damage plants, affect fresh water, and change the chemistry of rivers and lakes. Forests may have suffered serious damage as these changes continued. Plants that formed the base of many food chains began to struggle in different parts of the world. The warming climate caused many other changes. Ice that existed in colder regions became smaller. Weather patterns changed. Some places became much drier than before, while other areas experienced heavy rainfall. Many animals depended on stable conditions for food, water, and shelter. As these conditions changed, many species found it difficult to adapt quickly enough. The oceans also experienced serious problems. As the atmosphere became warmer, ocean temperatures increased. Warm water holds less oxygen than cooler water. Many sea animals depended on oxygen dissolved in the water in order to survive. As oxygen levels fell, large areas of the oceans became difficult places for life. Animals that could not move to better conditions began to die. Scientists believe that some parts of the oceans became almost completely without oxygen. This condition is called ocean anoxia. When oxygen disappears from seawater, many forms of marine life cannot continue living. Animals living on the sea floor were especially affected because they could not easily escape. Entire communities of sea creatures disappeared from many regions. The lack of oxygen also allowed certain kinds of bacteria to grow more easily. Some of these bacteria produce poisonous gases such as hydrogen sulfide. If large amounts of these gases entered the water and later reached the atmosphere, they could have caused even greater damage to plants and animals. Although scientists continue to study exactly how much hydrogen sulfide was released, many believe it played an important part in making conditions worse. The food chains that supported life slowly began to break apart. Tiny organisms floating in the oceans declined in many places. Animals that fed on them lost an important source of food. Larger animals then struggled because the smaller animals they hunted became fewer. As more species disappeared, the natural balance of many environments was lost. On land, forests were heavily affected. Fossil evidence shows that many plant species disappeared during this period. When forests became smaller, animals that depended on them also faced serious problems. Plant-eating animals found less food. Meat-eating animals then had fewer prey to hunt. Soil became weaker in some places because plant roots were no longer holding it together. Rain washed loose soil into rivers and eventually into the oceans, creating even more environmental stress. Many insects also experienced major losses. Insects are usually very successful at surviving difficult conditions, yet this extinction affected many insect groups. Scientists believe this is one of the few times in Earth's history when insects experienced such widespread extinction. Since insects play important roles in breaking down dead material, pollinating plants, and serving as food for other animals, their decline affected many parts of nature. The extinction did not happen in a single day or even within a single year. It unfolded over a long period. Some species disappeared earlier than others. Some populations became smaller over many generations before finally disappearing. Others may have survived in a few protected areas for some time before they also vanished. Fossil records from different parts of the world show that the timing of extinction varied slightly from place to place, but the overall result was the loss of an enormous number of living species. Scientists estimate that about 90% of marine species disappeared during this event. Many studies also suggest that about 70% of land vertebrate species became extinct. These losses affected almost every major group of living things. Entire branches of life's history ended, leaving behind only fossils as evidence that they had once existed. Many famous groups of ancient sea animals never recovered. Trilobites, which had survived many earlier changes in Earth's history, finally disappeared forever during this extinction event. Numerous coral species also vanished, and reef systems that had supported rich marine life were destroyed in many places. Brachiopods, which had once been among the most common sea animals, suffered enormous losses. Ammonoids, crinoids, and many other marine creatures also experienced severe declines. The story of the rise of dinosaurs and the age of reptiles began during a time when life on Earth was recovering from one of the greatest disasters in its long history. Before dinosaurs became the most successful land animals, the planet had already passed through many important changes. Huge numbers of plants and animals had disappeared, leaving empty places in nature. These empty places allowed new groups of living things to grow, spread, and develop into many different forms. Over a long period of time, reptiles became the most successful animals on land, and among them, dinosaurs slowly appeared and grew into a wide variety of species that lived across almost every part of the world. The world, during the early part of this time, looked very different from today. Almost all of Earth's land was joined together into one giant land mass. This made it possible for many animals to travel across large areas without crossing wide oceans. The climate over much of the land was warm, and many places were dry with long seasons that received little rain. Rivers, lakes, and green forests were found in many regions, while other areas were covered by deserts and rocky ground. The changing weather and the movement of the land helped shape the lives of the animals that lived there. The first dinosaurs appeared during the Triassic period, about 230 million years ago. They did not begin as the largest or strongest animals on Earth. At first, they were only a small group among many different kinds of reptiles. Some were no larger than a chicken, while others were about the size of a large dog. These early dinosaurs had long tails, strong back legs, and bodies that allowed them to move quickly. Many scientists believe that speed helped them escape danger and find food in a world filled with many competing animals. The ancestors of dinosaurs belonged to a larger group of reptiles known as archosaurs. This group also included the ancestors of crocodiles and flying reptiles called pterosaurs. Archosaurs had special features that made them different from many other reptiles. Their legs were placed directly under their bodies instead of spreading out to the sides. This body shape allowed them to stand upright and move more easily. Dinosaurs inherited this important feature, giving them better movement over long distances and making it easier to chase food or escape enemies. Early dinosaurs were not all meat-eaters. Some fed on plants, while others hunted small animals, insects, and other reptiles. Different eating habits helped them survive because they did not all depend on the same food. As plants changed and new forests appeared, plant-eating dinosaurs found more sources of food. Meat-eating dinosaurs also found more prey as animal populations increased. The plants growing during this time were very different from those that cover much of the world today. Flowering plants had not yet appeared. Forests were filled with tall conifers, cycads, seed ferns, horsetails, and many kinds of ferns. These plants formed large green areas where plant-eating reptiles could find food. Rivers and lakes often supported thick plant growth, creating places where many different animals gathered to drink and feed. Life during the Triassic period was not easy. Earth's climate changed from place to place, and many animals competed for food and living space. Large reptiles that were not dinosaurs often ruled the land. Some had heavy bodies covered with thick skin, while others were fast hunters with sharp teeth. Early dinosaurs had to survive alongside these powerful animals for millions of years before they became more successful. Many scientists believe that another major extinction event near the end of the Triassic period changed life once again. Many groups of reptiles that had dominated the land disappeared. The exact cause is still being studied, but huge volcanic eruptions are believed to have played an important part. These eruptions released large amounts of gases into the atmosphere, changing the climate and affecting many living things. As older groups disappeared, dinosaurs found new opportunities to spread across the land. After this extinction, the Jurassic period began about 201 million years ago. During this time, dinosaurs became the dominant land animals across much of Earth. They increased in number, size, and variety. Many new species appeared, each adapted to different environments and different ways of life. Some lived in forests, others lived in open plains, and many stayed close to rivers and lakes. The Jurassic world was warm, and many regions supported thick forests filled with tall trees. Large plant-eating dinosaurs moved through these forests in search of leaves and branches. Some grew to enormous sizes and became the largest land animals that had ever lived. Their long necks allowed them to reach leaves high above the ground. Their long tails helped them balance their huge bodies while walking. These giant dinosaurs belonged to a group called sauropods. Famous members included animals such as Diplodocus, Apatosaurus, and Brachiosaurus. Some reached lengths of more than 100 feet and weighed many tons. Even with their great size, they mostly fed on plants. They spent much of their time eating because such large bodies required huge amounts of food every day. Scientists believe that sauropods swallowed many leaves without chewing them very much. Their teeth were better for pulling leaves from branches than for breaking them into small pieces. Stones swallowed with food may have helped grind plants inside their stomachs. This allowed them to digest tough plant material more effectively. Large plant eaters attracted large meat eaters. During the Jurassic period, several powerful predators hunted other dinosaurs. One of the best known was Allosaurus. It had strong legs, sharp claws, and jaws filled with curved teeth. It hunted smaller dinosaurs and may also have attacked weak or injured large plant eaters. Like modern predators, it probably took advantage of opportunities rather than attacking only healthy animals. Not every dinosaur was enormous. Many small species lived in forests, near rivers, and across open land. Some hunted insects while others searched for seeds, leaves, fruits, and small animals. Smaller bodies allowed these dinosaurs to move quickly through thick plants and narrow spaces. They could escape larger predators by running fast or hiding among trees and bushes. Many dinosaurs lived in groups. Fossil evidence suggests that some species traveled together, especially plant eaters. Living in groups offered several advantages. Young animals could stay near adults for protection. Many eyes could watch for danger. Groups also helped individuals find food and move across large areas more safely. Dinosaurs reproduced by laying eggs. Female dinosaurs built nests in different ways, depending on the species. Some dug shallow holes in the ground before laying their eggs. Others carefully arranged plants around their nests. Fossils of nests and eggs found in many countries show that dinosaurs returned to safe nesting places during breeding seasons. Some dinosaur fossils show signs that parents cared for their young after they hatched. Adults may have protected nests from predators and stayed nearby until the young became stronger. Baby dinosaurs were much smaller than adults and faced many dangers. Meat-eating reptiles, early mammals, and even other dinosaurs could attack them. Parental care increased the chances that young dinosaurs would survive. Although dinosaurs ruled the land, they were not the only animals living during this time. Early mammals also appeared. These mammals were generally small and often active during the night. Many fed on insects, seeds, or small animals. Their small size helped them avoid large reptiles. They remained a minor group for millions of years, while dinosaurs dominated the land. Flying reptiles called pterosaurs filled the skies. These animals were not dinosaurs, although they lived at the same time. They had wings made from skin stretched between their bodies and a greatly extended finger. Some hunted fish along rivers and coastlines, while others searched for insects or small animals. Their sizes varied from small species with short wings to giants with wings wider than many modern airplanes. The oceans were also filled with reptiles, but these sea reptiles were different from dinosaurs. Ichthyosaurs had streamlined bodies suited for swimming and hunted fish and squid-like animals. Plesiosaurs had long necks and strong flippers that helped them move through the water. Mosasaurs appeared later and became powerful marine hunters. These sea reptiles spent nearly all their lives in water. During the Jurassic period, birds began to appear from small feathered dinosaurs. One of the earliest known birds was Archaeopteryx. It had feathers, wings, claws on its hands, and a long bony tail. Its body showed features found in both birds and small dinosaurs. Fossils of Archaeopteryx have helped scientists understand how birds developed from dinosaur ancestors. Feathers probably first evolved for purposes other than flight. They may have helped keep animals warm, attract mates, or protect eggs. Over time, feathers became useful for gliding, and later for powered flight in some species. Many small meat-eating dinosaurs had feathers long before true birds appeared. As millions of years passed, Earth's land slowly began to separate into smaller continents. The movement of these land areas changed climates, rivers, coastlines, and habitats. Different dinosaur groups became separated from one another. Over many generations, isolated populations developed into new species suited to their own environments. The Cretaceous period began about 145 million years ago. Dinosaurs continued to grow in number and diversity. New groups appeared, including horned dinosaurs, duck-billed dinosaurs, armored dinosaurs, and many advanced meat-eaters. Flowering plants also began spreading across the land, adding new food sources for plant-eating animals and creating new habitats for insects and other living things. Horned dinosaurs developed large bony frills and horns on their heads. These structures may have helped protect them from attacks, identify members of the same species, or attract mates. One famous horned dinosaur was Triceratops, which had 3 large horns and a strong bony frill protecting its neck. Duck-billed dinosaurs had wide mouths with hundreds of teeth suited for cutting and grinding plants. They could process tough vegetation efficiently and lived in large herds in many parts of the world. Fossils suggest that some species cared for their young in nesting colonies, where many families lived close together. Armored dinosaurs carried heavy plates or spikes covering their bodies. Ankylosaurus was protected by thick armor and had a heavy club at the end of its tail. This powerful tail could be used to defend against attacking predators. Among the meat-eaters, several species reached very large sizes. Tyrannosaurus rex lived near the end of the Cretaceous period and became one of the largest land predators known. It had powerful jaws, capable of crushing bone, large teeth, strong legs, and a massive body. Although it is often pictured hunting large animals, scientists also think it sometimes fed on dead animals when the opportunity was available. Another impressive predator was Spinosaurus, which lived in areas with large rivers. It had a long, narrow snout filled with pointed teeth suited for catching fish. Evidence suggests that it spent much of its time near water and may have been able to swim well. A tall structure along its back supported a large sail made from skin and tissue connected to long bones, extending upward from its backbone. Velociraptor was much smaller than many famous meat-eaters. It had sharp claws, feathers, and a body built for speed. Fossils suggest it was an active hunter that searched for smaller prey. Popular movies greatly increased its fame, although real Velociraptor was much smaller than shown in many films. Dinosaurs developed many different body shapes. Some walked on 2 legs while others walked on 4. Some had long necks while others had short, thick necks. Certain species carried horns, plates, spikes, or armored skin. Their teeth also differed depending on what they ate. Plant-eaters had broad teeth for cutting leaves, while meat-eaters had pointed teeth for gripping flesh. Scientists learn about dinosaurs mainly through fossils. Fossils form when plants or animals are buried by mud, sand, volcanic ash, or other materials before their remains completely decay. Over very long periods, minerals replace parts of bones or fill empty spaces, turning them into stone. Later, movement of Earth's surface and natural erosion expose these fossils where scientists can discover them. Excavating dinosaur fossils requires careful work. Researchers slowly remove surrounding rock, using small tools to avoid damaging the bones. Each fossil is carefully recorded, so scientists know its exact position. This information helps them understand how the animal lived and how it became buried. After fossils are removed from the ground, they are cleaned and studied in laboratories. Scientists compare bones with fossils found elsewhere. They examine teeth, joints, muscles, growth patterns, and injuries. Modern technology allows researchers to create detailed digital models of skeletons without damaging the original fossils. Fossil footprints provide valuable information even when bones are missing. Tracks preserved in ancient mud show how dinosaurs walked, ran, and sometimes traveled together. Long lines of footprints reveal movement across ancient landscapes. Some trackways show adults traveling beside smaller young animals, suggesting family groups. Fossilized droppings known as coprolites also help scientists understand dinosaur diets. Plant remains inside these fossils show what plant eaters consumed, while bone fragments found in others reveal the meals of meat eaters. These discoveries provide direct evidence about feeding habits. Scientists also study fossilized skin, feathers, eggs, nests, and even tiny marks left by diseases or injuries. Some dinosaur bones show signs of healing after being broken, meaning these animals survived serious accidents. Others display evidence of infections or bites received during fights with predators or members of their own species. Growth rings inside dinosaur bones help estimate age. Similar to growth patterns seen in many living animals, these rings show that some dinosaurs grew very quickly during their early years. Large species reached enormous sizes within relatively short periods before slowing their growth as adults. Scientists continue debating whether many dinosaurs were warm-blooded, cold-blooded, or had a body system somewhere between these conditions. Evidence from bone structure, growth speed, feathers, and activity levels suggests that many dinosaurs had higher activity than traditional reptiles. Research continues as new discoveries are made. The age of reptiles included many groups besides dinosaurs. Crocodile relatives lived in rivers, lakes, and wetlands. Some ancient crocodile relatives grew much larger than those living today. Turtles also became established during this long period and gradually spread into different environments. Lizards and snakes appeared later and slowly developed into many different forms. Insects also played important roles in prehistoric ecosystems. Beetles, dragonflies, flies, ants, and many other insects lived among the plants. They became food for birds, small reptiles, mammals, amphibians, and some dinosaurs. As flowering plants spread, insects helped carry pollen between flowers, supporting plant reproduction. The climate during the age of reptiles changed many times. Some regions became wetter, while others became drier. Sea levels rose and fell over millions of years, creating new coastlines and inland seas. Volcanic eruptions occasionally covered wide areas with ash. Earthquakes and mountain building changed landscapes. Living things constantly adapted to these changing conditions. The movement of continents continued throughout the age of reptiles. Large landmasses slowly drifted apart, opening new oceans between them. Animals that had once shared the same lands became separated. Isolation allowed different populations to develop unique features over many generations, increasing the diversity of dinosaur life. Plant life also changed steadily. Flowering plants became more common during the later part of the Cretaceous period. Fruits, seeds, and new leaf types provided additional food sources for many animals. Forests became more varied, supporting greater numbers of insects, birds, mammals, and reptiles. The age of reptiles lasted for well over 180 million years. During this long span of time, dinosaurs experienced periods of growth, change, and adaptation. Different species appeared, flourished, and disappeared long before the final extinction event at the end of the Cretaceous period. New discoveries continue to reveal that dinosaur life was far more varied and complex than people once believed. Fossils found across every continent, including Antarctica, continue to expand scientific understanding of these remarkable animals, their environments, their behavior, their growth, and their place in Earth's long natural history. The asteroid impact and the end of the dinosaurs is one of the most important events in the history of Earth. It changed life across the planet and marked the end of a very long period during which dinosaurs were the largest land animals. Before this event, dinosaurs had lived on Earth for many millions of years. They had spread across different continents and had adapted to many kinds of environments. Some lived in forests, some lived in dry lands, and others lived near rivers lakes, and coastal areas. They came in many shapes and sizes. Some were very small and light, while others were among the largest animals that have ever walked on land. Meat-eating dinosaurs hunted other animals, while plant-eating dinosaurs fed on leaves, branches, ferns, flowers, and other plant life. During this time, many other forms of life also lived beside them, including flying reptiles, sea reptiles, insects, fish, early mammals, birds, and many kinds of plants. The event that ended the age of the dinosaurs happened about 66 million years ago. Scientists believe that a very large asteroid from space struck Earth with tremendous force. This asteroid had been moving through space for a very long time before reaching our planet. It was part of the many rocky bodies that travel around the Sun. Most of these objects never come close to Earth, but from time to time, one enters Earth's path. When the asteroid that caused this event reached Earth, it was moving at an extremely high speed. It entered the atmosphere and rushed toward the ground in only a short time. The enormous amount of energy released during the impact changed the planet almost immediately. Scientists estimate that the asteroid was about 10 kilometers wide. Even though this may not seem very large when compared with the size of Earth, the speed at which it struck made the impact one of the most powerful natural events ever known. The asteroid hit an area that is now part of the Yucatan Peninsula in present-day Mexico. The impact created a huge crater known today as the Chicxulub crater. This crater remained hidden for a long time because it was buried beneath layers of rock and sediment. It was only after careful scientific studies that researchers discovered its full size and understood its connection to the disappearance of the dinosaurs. The place where the asteroid struck was covered by shallow seas during that time. The rocks beneath the water contained large amounts of sulfur, limestone, and other materials. When the asteroid hit, these rocks were broken apart and thrown high into the atmosphere. Huge amounts of dust, ash, rock fragments, and gases spread across the sky. The force of the explosion was so great that material from the impact was carried far beyond the area where the asteroid landed. Some of the hot rocks were thrown into space before falling back to Earth. The impact created an intense blast wave that moved across the nearby land and sea. Everything close to the point of impact was destroyed almost instantly. Plants were burned, animals were killed, and the landscape was completely changed. The heat released by the impact was so great that rocks melted. Some of the melted rock cooled while flying through the air and formed tiny round pieces that later fell back to the ground. These small pieces have been found in many places around the world, helping scientists understand how far the effects of the impact spread. Powerful earthquakes shook the Earth soon after the asteroid struck. These earthquakes were much stronger than those usually experienced today. The shaking caused landslides, cracks in the ground, and changes in rivers and coastlines. The force also produced giant sea waves known as tsunamis. These waves traveled across the oceans and reached distant shores. Coastal areas were flooded, and many living things near the sea were swept away. Evidence of these giant waves has been found in layers of rock in different parts of the world. As hot material from the impact fell back through the atmosphere, it heated the air over large areas of the planet. This caused many wildfires to start almost at the same time. Forests, grasslands, and other areas filled with plants burned over wide regions. Smoke from these fires mixed with dust and ash already present in the atmosphere. This made the sky even darker and reduced the amount of sunlight reaching the surface. The thick layer of dust and ash in the atmosphere blocked much of the sunlight for a long period. Without enough sunlight, plants could not carry out photosynthesis as they normally did. Photosynthesis is the process through which green plants use sunlight to make food. As plants struggled to survive, many began to die. This affected animals that depended on plants for food. Plant-eating dinosaurs found less food available. As they became weaker and their numbers fell, meat-eating dinosaurs also faced food shortages because their prey became scarce. The collapse of food supplies spread through almost every ecosystem. Small animals that depended on seeds, fruits, leaves, or insects also faced great difficulties. Many insects disappeared in some areas because the plants they depended on had died. Animals that fed on insects then found less food. This chain of events affected many different forms of life. Each loss led to another loss, creating widespread changes across land and sea. The oceans also experienced severe effects. Tiny organisms floating near the surface depended on sunlight just as plants on land did. When sunlight was blocked, many of these tiny organisms died. These small living things formed the base of many ocean food chains. As they disappeared, fish and other sea animals that depended on them also suffered. Larger sea animals then faced shortages of food. Entire marine ecosystems experienced major changes over time. The atmosphere itself changed after the impact. Dust, ash, smoke, and gases remained in the air for months, and possibly even years. During this period, temperatures dropped because less sunlight reached Earth's surface. Many areas became colder than before. Plants that had survived the first effects now faced new difficulties, caused by lower temperatures and shorter growing seasons. Many could no longer survive under these conditions. Scientists believe that acid rain also formed after the impact. Gases released into the atmosphere mixed with water vapor and later fell as rain containing harmful acids. This rain damaged plants, affected lakes and rivers, and created additional problems for living things already struggling to survive. Freshwater environments experienced many changes as water chemistry shifted. Many dinosaur species disappeared during this period. Large plant-eating dinosaurs could not find enough food to support their huge bodies. Large meat-eating dinosaurs lost the animals they hunted. Eggs and young dinosaurs may also have been especially vulnerable because changing temperatures and harsh environmental conditions made successful breeding much more difficult. As older animals died and fewer young survived, dinosaur populations continued to decline. Not every kind of dinosaur disappeared. Modern birds are descendants of a group of small feathered dinosaurs that survived the extinction event. These early birds possessed certain features that may have helped them stay alive. Some were able to eat a wider range of foods, including seeds that remained available even after many plants had died. Others may have found shelter in places less affected by fires or sudden changes. Over many millions of years, these surviving birds continued to evolve into the many bird species found around the world today.